My name is Brayan. I'm from the University of Alicante and I'm going to present you our work entitled Prediction of Tactile Perception from Vision on Deformable Objects. Tactile perception is being used in robotics for tasks like predicting the stability of a grasp, like in this case down here, in which we grasp an object and we want to know if it's going to be stable or it's going to be unstable in our hand. But it's also being used for recognizing textures of objects, like if we grasp the object and we want to recognize properties of it to recognize which object it is. But all of these applications require the tactile sensor to come into contact with the surface. That is, if the sensor does not contact the object or the surface is not going to register anything for it. But humans can predict how an object feels by looking at it. If we see at this bottle of here, we know how it feels if we grasp it, we know how it reacts our touch. Can we provide robots with such a skill, and how precise can we be for deformable objects? Like in this case, we want the robot to know how it feels if it crosses this object at this point, so that is, we want to know how the two tactile sensor and its fingers are going to behave. For this task, we are using two BioTAC SP sensors, one in the thumb and another one in the middle finger of a shadow hand. This tactile sensor registers one general pressure value in its base, right down here, but it also registers 24 electrode values, with these electrodes throughout its surface. So our goal is to learn to regress these values, either the electrode values or the PDC value, the pressure value, from visual clues of the objects plus the grasp information of the grasp that we want to execute. For this task, we are proposing the use of the SR-GAN, which is a GAN network used for regression learning and semi-supervised learning, which was proposed by Olmshenk et al. At 2019. This GAN has a discriminator that is going to learn a regression task, in this case regressing PDC values or the electrode values, and it uses the pointed feature calculator for learning features from our point clouds of objects. So we are going to have a simple label data, which are clouds of objects, with grasp data, that is the grasping points plus the orientation of the hand, and all of this information is going to help the discriminator learn the task. But label data also has labels, which are target regression values. But this is a semi-supervised learning system, so it also has unlabeled data in which we have point clouds with grasp information but no target tactile responses. And since it is a GAN network, we also have a generator that is going to produce fake clouds for us, so we can have fake data, that is clouds and grasp data as well, but no target tactile sensor. So these two types of data are supposed to improve the performance of the system. And for this, we are going to compare the SR-GAN with these three types of data with a system training with this network up here, only trained with label data, which is our baseline. For this comparison, we have collected a dataset with 4 objects. In total, we have 3,200 training samples that we have split in these 5 sets with different ratios of labeled and unlabeled data. So for example, the T10 means that the 10% of the training samples are unlabeled, so we don't have a label here, and the remaining 90% are labeled samples. Using this, we have compared the baseline, which is this discriminator trained with labeled data only, which is a pointed, with the SR-GAN on the 4 modalities, that is the PDC, the general pressure value, and the electrode values for the thumb and for the middle finger. And on average, we can see that the SR-GAN improves the performance of the pointed in at least 3 out of 5 experiments. Like in this case, it improves it in 1, 2, and 3, and 4 experiments, although there are examples of cases in which it cannot improve it just once. And however, the peak performance of the system was achieved with pointed. So in conclusion, we can say that the best performing models are only 6% error points off from the actual tactile response. These are still early results since we are using a small data set, and deformable objects are really hard because their appearance might not directly relate to their stiffness, so we want to continue experimenting with more objects, including solid objects.